Hello everyone. In this video I am going to discuss about the problematic part from the stresses and deflections of helical coil springs, which we have discussed earlier. This is from the topic mechanical springs from the course DMM1. Now see the problem. A helical spring is made from a wire of 6 mm diameter and has outside diameter 75 mm. If the permissible shear stress is 350 MPa and modulus of rigidity 84 kN per mm square, find the axial load which the spring can carry and deflection per active turn. These two we need to find out by using this data. Now see the given data. Diameter of wire 6 mm, outside diameter of the spring d0 is equal to 75 mm, shear stress 350 MPa, that is equal to 350 Newton per mm square, and modulus of rigidity capital G is equal to 84 kN per mm square, which will be equal to 84 into 10 cube Newton per mm square. Now we need to find out the dimensions of the spring. We know that mean diameter capital D is equal to d0 minus 2r or d0 minus d. From the outside diameter, if you remove the radiuses, we will get the d value, mean coil diameter, which you have learnt here. That will be 69 mm, and spring index C is equal to capital D by small d. Capital D we find out 69 mm, which is mean coil diameter, and small d already given 6 mm, which will be 11.5. W is the axial load and delta by n is the deflection per active turn. Now we need to find out the deflection value. See, this first case was without the effect of curvature, that is thus Wahl's factor will be there, right, for stress concentration. We are neglecting the stress concentration and finding out these values. If we neglect this, we use this Ks value, which is the shear stress factor 1 plus 1 by 2c. We have to find out this Ks, shear stress factor, and then substitute this Ks factor in the equation of tau. Tau is equal to Ks into 8WD by pi d cube. If you substitute all these values, Ks you have to calculate, then we get this value in terms of W, and tau is already given in the problem, 350 Newton per mm square. Then we get W value. Okay, by using this W, we have to find out the deflection per active turn. Delta is equal, first you need to find out the delta, 8WD cube n by GD power 4. Then deflection per active turn will be delta by n, number of turns n, 8WD cube by GD power 4, n term will be removed. We got 9.96 mm, okay, in this case, without considering those stress concentration. And here we are finding out with considering the stress concentration and all, that is considering the effect of curvature. We know the Wahl's stress factor K is equal to 4c minus 1 by 4c minus 4 plus 0.615 by c. By using this, we have to calculate the K value 1.123, and now we have to find out the W value, which in the similar way, K, by using this relation, tau is equal to K into 8WC by pi d square. We substitute all the values, this term will be in terms of W, and tau value already given, shear stress to 350. Then we can find out the value W, which is 383.4 newtons. By using this value, we can find out the deflections per active turn, delta by n, 8WD cube by GD power 4. And by substituting these values, we get the deflection per active turn 9.26 mm. Okay, this is how we will find out the deflections per active turn. See the next problem. Design a spring for a balance to measure 0 to 1000 newtons over a scale of length 80 mm. The spring is to be enclosed in a casing of 25 mm diameter. This is the limit or the size they have in that particular case or application. There is only 25 mm diameter space in which you need to enclose a spring. Okay, the approximate number of turns is 30. The number of turns is also given 30. The modulus of rigidity is 85 kN per mm square, G value given. Also calculate the maximum shear stress induced. You have to design the spring, that means you have to find out the dimensions, and also you have to calculate the maximum shear stress value. So see the given data. In the first step we are doing the design. Capital D is the mean coil diameter of the spring and small d is the diameter of the spring wire. You know that spring index C is equal to capital D by small d, and he is also specified that the spring should be enclosed in a 25 mm diameter space, that is D naught should be, which is capital D plus D small d, which should be less than 25 mm. Okay, we know that delta is equal to 8wc cube n by ZD. This is the equation for deflection. Substitute all the values we have, then we have to find out this small d value. Okay, W already given 1000, and then number of turns given 30, and G value given. D is the unknown value, and this is shear stress value given 80. Sorry, this is deflection value. Delta is equal to 80 mm. We got 240 c cube by 85 d. From this we have to find out the c cube by d ratio, 28.3. Now we need to assume some value for this diameter, small d, diameter of the spring wire. Let us assume that d is equal to 4 mm. You can assume any value, 5 or 6, because the outside diameter should be 25 mm. The inside diameter of the spring should be half of this. Based on those metrics you can assume this d value. Okay, c cube is equal to 28.3 small d, where we have assumed that small d is 4 mm. Then we get c is equal to 4.84. Substitute these values, you get the capital D value, which is mean coil diameter. We know that the outside diameter of the spring is D naught is equal to D plus D, that is equal to 19.36 plus 4, 23.36, which was less than this 25 mm. So our assumption of wire diameter 4 mm is correct. Okay, then we need to find out the maximum shear stress value. We know that wall stress concentration stress factor K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by C. We need to find out this K value in order to find out the tau maximum shear stress. We got 1.322. We know that tau is equal to K into 8wc by pi d square, that is equal to 1.322 into 8 into W1000. C value 4.84 by pi into D we have already found out 4. We assumed that, and that was the correct 4 square. We got the maximum shear stress value of 1018.2 Newton per mm square, or 1018.2 megapascal. This is how we will find out these values. Next is the third problem. Design a helical compression spring for a maximum load of 1000 newtons for a deflection of 25 mm using the value of spring index as 5. C value is 5. The maximum permissible shear stress for spring wire is 420 MPa or 420 Newton per mm square, and modulus of rigidity is 84 kN per mm square. Okay, this is the Wahl's factor. K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by C. You need to design this helical compression spring using this data. Now see the given data. W is equal to 1000 newtons, deflection 25 mm, spring index 5, shear stress 420 megapascal, which is 420 newton per mm square, and modulus of rigidity 84 kilonewton per mm square, which is 84 into 10 cube newton per mm square. First we are finding out the mean diameter of the spring coil by using the shear stress equation. Tau is equal to K into 8WC by pi d square, where K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by C, which is 1.31. And by substituting these values, the known values, shear stress 420 Newton per mm square, 420 is equal to K into K already found out 1.31 into 8 into 1000 into 5 by pi d square. The d was the only unknown value. We get the d as 6.3 mm from this relation. If there is any standard table given, you can select the diameter from the standard table. This SWG will be, this is grade G3 will be grade 3, SW will be spring steel wire. There are two types, SW and VW. SW will be spring steel wire and VW will be wall spring wire. This SWG3 will be 6.401. Okay, for the similar data. Next, mean diameter of the spring coil we need to find out using this relation, which is C is equal to capital D small d spring index. Capital D is equal to C into small d, 5 into D, which will be 32.005 mm. And the outer diameter of the spring will be D naught is equal to capital D plus small d, 32.005 plus 6.401, that is equal to 38.406 mm. Next we need to find out the number of turns of the coils. We know that tau is equal to 8 WC cube n by ZD. Delta is equal to 8 WC cube n by ZD, that is equal to, all the values are given. By substituting these values we can find out the n value, deflection. This is for squared and ground ends. The total number of turns will be n dash is equal to n plus 2. Here n is 14, we got here, that is equal to 16. 14 plus 2, 16. Next we need to find out the free length of the spring. We know that free length of the spring is equal to solid length plus deflection plus the overall gap between the coils, 0.15 D. By substituting all these values which you have found out earlier, n dash is 16, D already we have found out 6.401 plus 25 already given, deflection plus 0.15 into 25, we get 131.2 mm. Next pitch of the coil will be free length by n dash minus 1, 131.2 by 16 minus 1. Free length we have already found out here, 131.2. Substitute this n dash minus 1, we get 8.75. This will be the pitch of the coil. If the design problem is given on helical compression spring, you need to find out all these: mean diameter of the spring coil, number of turns of the coil, free length of the spring, and pitch of the coil. Next, see the problem 4. Design a closed coil helical compression spring for a service load ranging from 2250 newtons to 2750 newtons. The axial deflection of the spring for the load range is 6 mm. Assume a spring index of 5. The permissible shear stress intensity is 420 megapascal or 420 newton per mm square, and modulus of rigidity G is equal to 84 kilonewton per mm square or 84 into 10 cube newton per mm square. Neglect the effect of stress concentration. Draw a fully dimensioned sketch of the spring. Show details of the finish of the end coils. This is the design on the closed coil helical spring. Now see the given data W1 and W2. W1 is equal to 2250 newtons and W2 is 7250 newtons. This is the range. Delta deflection given 6 mm, spring index 5 was given, shear stress 420 Newton per mm square, and modulus of rigidity 84 into 10 cube Newton per mm square. Now we need to find out the mean diameter of the spring coil. Okay, we know that twisting moment on the spring, or torque is equal to load into the distance. T is equal to W. Here we are taking the maximum load 2750. If the spring can resist this maximum load, the spring, the design of the spring will be safe. Okay, so based on the maximum load we are designing the spring. Torque is equal to W2 into D by 2. 2750 into capital D will be C in C by small d, right? That capital D will be C into small d, that will 5 times small d, 5d by 2, 6875 d in terms of the torque will be in terms of d. And we also know that from the torque equation, T by J is equal to tau by R. We got this relation. Okay, this is T is equal to tau ZP. Tau into the ZP will be pi by 16 d cube, polar section modulus. Tau into pi by 16 d cube. We got this. We know that already the tau value was given. The d was the only unknown value. We can find out the d value using these two relations, two equations. Using these two relations, you can find out the d value. D is equal to 9.13 mm. There is any standard tables given. You can select the standard wise size from that standard table, or you can simply take the value 9.13 mm. Next, mean diameter of the spring coil, capital D is equal to 5 times D by using spring index relation. We get 47.45 mm. We know that outer diameter is equal to D naught is equal to capital D plus D. See, this D naught will be this capital D is mean coil diameter plus here we have some radius R and here we have some radius. If you add with those two radius, capital D plus small d, we get the D naught value. D naught is equal to capital D plus small d, 47.45 plus 9.49, which will be 56.94 mm. We want to find out the inner diameter. Di is equal to capital D minus small d, 47.45 minus 9.49, which will be 37.96 mm. Next, we need to find out the number of turns by using the delta by n relation. Deflection delta is equal to 8WCQ1 by GD. By using this relation, substituting all the known values, we can find out the n value, because we know the deflection delta is equal to 6 mm given W see, it is given that axial deflection for the load range from 2250 newtons to 2750 newtons. Which will be m was for the 500 newtons load. Okay, so we are taking that W as 500 newtons. In this case, 500 into 5 cube into n. By using this, we get the n value as 10. And for square and ground ends, this end, if you want the square and ground ends, the total number of turns should be n dash, which will be n plus 2. The n we got 10, 10 plus 2 will be 12. Next, free length of the spring. Since the compression produced under 500 newtons is 6 mm, therefore maximum compression produced under maximum load of 2750 newtons is delta max is equal to 6 by 500 into 2750, which will be 33 mm. Okay, the maximum deflection will be 33 mm if you want to find out for 2750 newtons. We know that free length of the spring is solid length plus maximum deflection plus the maximum gap, actual gap. Okay, 12 into 9.49 plus 33 plus 0.15 into 33, which we will get 152 mm. Pitch of the coil will be free length by end dash minus 1. Free length was 152 mm and end dash 12 minus 1, which will be 13.8 mm. After all this, you need to draw this figure by specifying all the dimensions which was asked in the problem. The total length will be 152 mm and the pitch of the coil, the distance from one coil to another coil, will be 13.8 mm. This is how you will do the problem. Thank you. For this problem's reference, you can check RS Kurmi Mission Design Textbook. Thank you.